So good morning and welcome for another session for calculus. Let's see, we've got a couple of points today, so I would like to address the questions first of all that you put up in Canvas. Then I'll give a short recap of what we have done on Monday, and then I'll go back to the week 5 material. And as you know, tomorrow is the midterm, and in the meantime, you have had a lot of information about the midterm already. There was a very long email. I've seen a copy of it. So hopefully you feel well prepared and you know what is expected of you. If not, ask me in the chat room on YouTube. But once again, and we'll get to that when I address the questions in Canvas too. If you have questions about the organizational details, don't put them to me, just the mathematical questions. So everything related to the organization of the midterm, please ask them at the general email address calculusabc@tue.nl. So let's go and see what questions there were in the meantime on Canvas. So I'm going to switch and let you see the questions too. That should be here. Yep, excellent. So here are the questions from the beginning. So can you also give your explanation in Dutch at the midterm? To be on the safe side, English is always fine. Not all of the tutors speak Dutch. I am not sure if it is allowed. That's typically an organizational question, so you can send an email to calculusabc@tue.nl. In the email, it says that you can write your answers down and upload pictures afterwards, but it doesn't correspond with the proctoring document. So after the test, after you have submitted your test, you will have half an hour to upload your answers to Canvas. So you have the test, and then afterwards there is additional time in which you can upload your answers to Canvas. Where can we make a practice exam with Proctorio? In answer, the 4 practice with Proctorio exams are not available for us. Ask that question to calculusabc@tue.nl because I'm not involved with that, so I can be an in-between, but that's probably better if you ask it directly there. Okay, and here is a mathematical question. I do not understand the following. When you have to simplify an expression like exercise 57 of section 0.3, I checked that should be 0.4, but it's okay. Cosine, arcsine, and then it says a half, that should probably be x. You have to state the range of x's for which it holds. How do you do this? So let's have a look at that. You have already seen a couple of these questions, this type of question. So let me switch to my iPad. Perfect. And the question we have here, so just to add to that, if you would like to look it up, this is section 0.4, and then it's question 57. So the question we're being asked is to simplify the cosine of the arcsine of x. So the general strategy that we've already seen a couple of times is that you say, well, let's call this thing here in between the brackets, let's call that theta. So then we have the arcsine x equals theta. So that means that the sine of theta equals x, because they're each other's inverses, right? And I'm first going to solve it as we did before. So I'm going to say, well, let's draw a little triangle with an angle theta and a 90-degree angle. The sine equals x. So the sine, that is the length of this side over the length of this side. So I'm labeling them x and 1. And then using Pythagoras, we know that the length of basically the missing length here is going to be the square root of 1 minus x squared, because if you then apply Pythagoras, then you immediately see that square of the square root of 1 minus x squared plus x squared equals 1. So then Pythagoras holds. And now we just read off the answer because we were being asked for the cosine of theta, which is now, if you look into this little triangle, it's the length of the adjacent side, square root 1 minus x squared over 1, which is square root 1 minus x squared. Okay, so that was how we solved it previously. And now the additional question that Jana had is, how can you tell for which axis this holds? Now, if you look what I did here, when I was basically doing this stuff here, well, first of all, here we took the arcsine of x. So that means that x should be in between minus 1 less or equal x less or equal 1. Otherwise, I cannot do the arcsine. So the arcsine can only be computed for a number in between minus 1 and plus 1. But then additionally, if I'm drawing this triangle here, so if I am drawing this triangle, well, for the triangle to make sense, the x value should be in between 0 and 1. So here we have like 0 is less than x is less than 1, because x is now a length in a triangle, and the length needs to be positive. So it cannot be 0. And if you would have 1, then this side would have length 0, which is also strange. So the triangle makes sense for x in between 0 and 1. Okay. Now, based on all of what it says here, what we have basically found now is that for 0 less than x less than 1, we find cosine arcsine x equals square root 1 minus x squared. Okay? And now we're going to see, can we extend this a little bit? So in principle, if you would look at this bit only, then x would have to be in between minus 1 and plus 1. Okay? So I would like to extend it to that range. So what you can do is that you say, well, let's first look at these limiting cases. So if x equals 0, well, on the left side, we have, first of all, we need arcsine of 0. Now, if you look back at when we talked about arcsine, it's the inverse of the sine function. And then you see that we would find 0 here. Now, the cosine of 0 equals 1. And also the square root of 1 minus x squared. For x equals 0, that's also 1. So we see that the formula still holds for x equals 0. Similarly, if you would pick x equals 1, you find that the arcsine of 1 is what we need. Now let me get some more paper here. So x equals 1 gives the arcsine of 1. And if you recall, then we were looking, if you have the sine function that goes approximately like this, and we are now interested in the arcsine of 1. So then we find pi over 2. It always helps to make a little drawing like this, that you know which angle you should pick. And then we find that the cosine of pi over 2 equals 0. The other formula was this, which is also 0. So apparently the formula that we have derived holds. So we have now found that cosine arcsine x equals this thing, for 0 less or equal x less or equal 1. And then finally, I would like to extend this to the whole range from -1 to +1. Now, what you see is that if you replace x by minus x here, then you would get a minus sign here, and the cosine of minus an angle is the same as the cosine of plus that angle. Here, it also doesn't matter if you're going to replace x by minus x. So, also holds for minus x. So the conclusion is that the equation is true for -1 less or equal x less or equal 1. So that is how you can find that. So you see, it's a bit of boring bookkeeping, but this is what is being asked in the book. So if they want you to find all the x's for which this equation holds true, this is how you should proceed there. So first look at for which x values the drawing makes sense, and then see if you can extend the formula that you found and see for which axis it holds true. Okay, so that's for Jana's question. Let me quickly go back to the questions. Those are here. So how do you make a vector representation of a plane given by 3 points? Okay, so what you should do here, so we are given 3 points here. Let me quickly write them down so that I take the same numerical values. So given are 3 points in space, and I'm copying them here, and I'm going to switch to my iPad in a second. So we have 1, 0, -1, 2, 3, -1, and we have 4, -1, 0. So the way you would proceed here, if you want a plane that goes through these points, what you do is you're looking for a vector equation, x, y, z equals, and then first you should have one point that is in the plane. So let's take 1, 0, -1, and then plus lambda times some direction vector plus mu times some direction vector, and lambda and mu can be any number because it's a plane. We can move in the plane, right? Now, for the direction vectors, what you should have is that if you have this plane here, you should have vectors A and B that are in the plane. Now, how can you do that? Well, you can simply say for A, I'm going to pick 2, 3, -1, -1, 0, -1. Because that is a vector that points from the first to the second point, from 1, 0, -1 to 2, 3, -1. And similarly for B, I could pick the vector 4, -1, 0, -1, 0, -1. Because that is a vector that points from 1, 0, -1 to 4, -1, 0. So that will be a second direction vector. And then we have a vector equation of the plane. And we have already seen a number of times how you can get from this vector equation to the standard equation. Basically, you have to get rid of the lambda and the mu. You write it out in components and you try to eliminate, try to remove lambda and mu from the equations so that you have an equation that only involves x, y, and z. Okay? Great. So let's switch back to your questions. Could you please explain how they got the normal vector of the plane in question 5b from the midterm? Let me check quickly if I can find that. So the midterm is on Canvas. So let me go there. So 5B Industrial Design 2019. Okay, let's go there. Okay, let's click here. And then in study materials, we have the exams. And then here we have industrial design midterm 2019. Oh, that opens up PDF. I should be able to show you the PDF like this, I guess. Yeah, that works. Excellent. So 5 B. Okay. So the plane at Z equals 10 is a solid flat object. So if you want to have the normal for that, okay. So Z equals 10 is a special case of the equation ax plus by plus cz equals a constant. So you can immediately read off that the coefficient for x is 0, for y is 0, and for z equals 1. So 0, 0, 1, that is a normal of this plane. So if I want to elaborate a little bit on the iPad here, let's add a page. So if you would have minus x plus 3y plus 2z equals 10, then you can immediately read off that the normal is minus 1, 3, and 2. So you just read off the coefficients of x, y, and z. So if you have the plane z equals 10, as it says here in this question, then you would find as a normal 0, 0, 1. So that's how you do it here. Okay? Okie-doke. Let's close this one. And let me switch back to the questions, but now I have to move back here. I know you cannot see it, but I'm deliberately leaving the screen on the iPad for a sec. Okay, here we go. And the questions, and close the menu, and then we're back. So I'm switching back to your questions here. Perfect. Okay. Hey, new questions are popping up. That's interesting. The line L passes through 4, 4 and minus 4, 0. Provide an equation for this line in the form ax plus by equals c. So the way you could do that, what is easiest, is just to plug in these values. So let's see. So we have the point 4, 4 and the point minus 4, 0. And we are being asked for an equation of the form ax plus by equals c. Okay. Let me switch to iPad. Okay, here we go. So what you can do here is just plug it in. So you find that if you just plug in these values, we are being asked for A, B, and C. And of course, there's some redundancy in there, right? Because you can divide the whole equation by C, for instance, to get a 1 on the right-hand side. So if I plug it in, I get 4A plus 4B equals C. That's for the first point. And for the second one, I find minus 4A plus 0 equals C. Okay. So apparently, if I find that A is minus C over 4, if I add these two equations together, I find that 4b equals 2c. So b equals 2c over 4 is c over 2. So apparently what I find is that minus c over 4x plus c over 2y equals c. And you can pick any c value here. So you could, for instance, pick c equals 4 to get some nice numbers, or c equals 1. But for every non-zero c, you would have a valid equation for the line. Okay. Switching back to the questions. I'm very confused, that's not good, about application 7 of section 3.3. You have to find a value of x that maximizes the viewing angle A. There is a picture. Only a solution of edition 4. That's a bit too detailed to go into now. I'll have a look in the break, and maybe at the beginning of the second hour I'll treat this one, but I'm going to skip it for now. Question 5b from the midterm. We already did a little bit on that, so hopefully that helps you, and there are solutions provided, right, on Canvas. If you have more specific questions, please ask. How should you solve this? What is the best tactic? Find the zeros of, and then basically a third degree polynomial. So the main idea for this type of questions, if you have a polynomial of degree 3, is to try and find one of them and then try simple values. So 0, x equals 1, x equals minus 1, x equals 2, x equals minus 2. You should be able to find one of those. So can we quickly see one here? Probably if you take, what is it, minus 1 or something like that, you should be able to have one. And then you write it as, if you find that, for instance, x equals a is a 0, you try to write this as x minus a times a polynomial of degree 2. And then a polynomial of degree 2, once you have found that, you know how to find the zeros of that. Okay. In the email about the midterm, it says that you can write your answers down and upload pictures afterwards. Oh, we already did that. They're in a different order now, the questions, because I left them and came back. This is Jana's question that we already did. This is the vector representation that we did. The normal vector, yeah, covered that. Where can you find the answers of questions or in the presentations? I'll upload them later on. I didn't do that before. If you have specific questions, just let me know. But I have answers there, and I'll put them in every week next to the slides. Okay, so where I put the slides, where you can find the PDF of the slides, I will also upload the answers there. Okay, so those were the questions for now. Only this one question I still have to address, and I'm going to make a note of it, because then I can start a new round so that these questions disappear. So application 7.3.3. Let me make a note of that, and then I'll come back to that. So 3.3 and then application 7. So I'll get back to that. And then here I'm going to start a new round of questions, since these are dealt with plus. Okay. And it's clear again. Okay. So let's go to what we have been covering on Monday. So on Monday we were talking about exponential and logarithmic functions. And what we have seen is basically the graph of an exponential function. So it goes, as our prime minister called it, like a hockey stick. You have very fast growth. And as a kind of characteristic, so normally we will always be dealing with e to the power x, because that is, in a sense, the nicest function for exponential growth. And we have seen that is basically due to, if you compute the derivative, if you do e to the power x, the derivative is e to the power x, and if you have some other power, like 4 to the power x, as we have here, you get an additional constant there. So that's a bit messy. So e to the power x is like the natural function, but all of them, if you take a base that's bigger than 1, all of them have this behavior that they go through the point x equals 0, y equals 1. They have a horizontal asymptote for x going to minus infinity, and they go to plus infinity for x going to plus infinity. You also see that they're increasing and always positive. So those are characteristics for all the exponential functions. We have also seen that if you make the requirement that the tangent line at x equals 0 should have slope 1, then you can define the constant e, which is like 2.718 and so on, Euler's number. I hope you watched the video by James Grime, that's very nice. And we have seen that since the function is increasing, it is 1 to 1, which means it has an inverse, and the inverse of the exponential function is the logarithmic function. In particular for e to the power x, so for the exponential function with base e, we have the natural logarithm, which we denote with ln, so we write ln there. So here's the graph of the logarithm. So we like to deal with the ln, but you can talk about the logarithm for different bases, like 2 and 10 as it's plotted here. They all have the same shape, and they go through the point x equals 1, y equals 0, and they're also increasing. And then this was more or less to illustrate to you why logarithms are so useful, because you can have multiplication, you can transform that to addition, and addition is a lot simpler than multiplication is. So this was the basic idea, and the slide rule is based on that, that if you go from x and y, you take the logarithm, you go to u and v, you simply add them, and then you go back. And then you can do multiplication of very big, complicated numbers. So here is that property, log x plus log y is the log of x times y. And then as a particular case, apparently an exponent, so x to the power y, you can write the y in front of the logarithm. And then as a kind of special case, again, if you have a quotient, you get a minus sign there. Finally, we have seen that every exponential function can be written as e to the power something, and every logarithm can be written as an ln, with also a constant in between there. And using this, we moved to the derivatives. And you can see that the derivatives are very nice for the exponential function e to the power x and for the natural logarithm. And if you have a different base, then you get funny constants there. Okay. So that is a wrap-up of what we have seen on Monday. Now, the next topic that I would like to discuss is a little bit of an application, as you might say. So I promised you that we would be talking about Gaudi. And we will be doing so. So to get there, first a little bit of a sidetrack. So what is an even function? A function is called even. Of course, you know even from numbers, right? 2, 4, 8, 10, those are even numbers. If you can divide it by 2 and you still get an integer, then it's an even number. For a function, it's a little bit different. The cosine function is even. So what is the defining property? The property is that if you do the f of minus x, you should find the same as the f of x. And what that means, if you look the interpretation, is that if you mirror in the vertical axis, in the y-axis, that it's symmetric, the function. So here you see that if you take this part of the cosine function and you mirror in the vertical axis, you get the same thing back. So x squared has that same property. And this is where the even comes from. If you take x to the power 4, x to the power 6, x to the power 10, x to some even power, then you have an even function. So that's where this name comes from. And as you see, the graph of an even function is symmetric in the y-axis. Now, if you have even functions, you also have odd functions. So what is an odd function? An odd function is a function that behaves like the sine, which means that if you take the f of minus x, that you get minus the f of x. So in the picture, the sine function is odd, x to the power 3 is odd, x to the power 5, x to the power 7, x to some odd power is an odd function. Okay? And what you see here, the symmetry, there's also symmetry. It's a bit more complicated. It is a point symmetry in the origin. So if you take the origin here, and if you would take some point here on the graph, if you would mirror that into the origin, then you get another point that is on the graph. So that's the idea for an odd function. Now, as you know, if you take a function like, for instance, let's say the square root function, or the exponential function, or the logarithm, most functions are not even and also not odd. So it's not with numbers. If numbers, a number is even or odd. But with functions, only very special functions are even or odd. Most functions are neither. They don't have these symmetry properties. But there is something funny, because if you take any function, so for instance the square root function, the square root is not very good because I want to talk about f minus x. Say the exponential function, we've just been talking about the exponential function. Then from this function that is neither even nor odd, we can define an even function using that function. So if you look at this thing here, so f is any function. It does not have to have any symmetries. But if you then define this function here, fx plus f minus x, you immediately see that if you replace x by minus x, that you get the same expression. So this thing here is an even function. And similarly, if you look here, and if you replace now x by minus x, you see that you get minus what it says here. So this is an odd function. So from any function, you can define an even function and an odd function, and, which is even more special, you can write your function, your general function, say e to the power x, as the sum of an even function and an odd function. So what you see is that this bit here is an even function, this bit here is an odd function, and if you add them together, you have your original function back, because here it says a half fx, here is another half fx, and this thing, they cancel. So any function can be written as the sum of an even and an odd function. Now, if you do that for the exponential function, then you get functions that have a name themselves. So if you do that for e to the power x, then the even part is called the cosine hyperbolic, and the odd part is the sine hyperbolic. So this is just a definition. If you work with these functions, usually it is most convenient to just go back to these definitions. For instance, if you want to differentiate them, it is easy to differentiate the exponentials, because we know that if you differentiate e to the power x, you get e to the power x. So here is the definition again, and a couple of properties. So what you see here is, well, by definition, the cosine hyperbolic is an even function, sine hyperbolic is an odd function. And you can see that from the definition. So as I said, for instance, if you look here, the cosine hyperbolic of minus x, well, the definition is here on the left. So if I just plug in minus x, you get e to the power minus x plus e to the power minus minus x, that's x, over 2, which equals cosine hyperbolic x. And similarly for the sine hyperbolic. If you are going to differentiate it like here, then you get the d dx cosine hyperbolic x is the ddx e to the power x plus e to the power minus x over 2 is the, say, 1/2 ddx e to the power x plus ddx e to the power minus x, which is 1/2 e to the power x minus 1/2 e to the power minus x, which is sine hyperbolic x. So they look like cosine and sine, but as you see, you don't get a minus sign here. So if you differentiate cosine function, you get minus the sine, but for the cosine hyperbolic, you find plus sine hyperbolic. And in the same way, you find that the derivative of the sine hyperbolic function equals the cosine hyperbolic. Then this last one, cosine hyperbolic squared minus sine hyperbolic squared equals 1. Let's also do that one. So cosine hyperbolic squared x, that is e to the power x plus e to the power minus x over 2 squared. Actually, I'm going to do that on the next page. I need a bit more space to write clearly. So what I want to show is that cosine hyperbolic squared x minus sine hyperbolic squared x equals 1. Now, cosine hyperbolic x is e to the power x plus e to the power minus x over 2. And then if you square it, you get 1 over 4 times e to the power x plus e to the power minus x squared, which is 1 over 4. And if you multiply, then you get e to the power 2x plus 2 e to the power x e to the power minus x plus e to the power minus 2x, which equals 1 over 4 e to the power 2x plus 2 plus e to the power minus 2x. Similarly, sine hyperbolic x is e to the power x plus e to the power minus x over 2. If you square that in completely the same way, you find 1 over 4 e to the power 2x minus 2 plus e to the power minus 2x. Oops, I forgot a minus sign, sorry. There should be a minus sign here. Like this. And then if you add them together, you find that, you subtract them. You find that cosine hyperbolic squared x minus sine hyperbolic squared x equals 1 over 4, 2 plus 2. All the other terms drop out if you subtract these things, which equals 1. So that's how you can find that, how you can work with these functions. And you see that the relations between cosine hyperbolic and sine hyperbolic, they resemble somehow cosine and sine. So that's one of the reasons that they have these names. Now, I promised you some nice things with these relations. And to get there, let's first look at the graph of these functions. So to get the graph of the cosine hyperbolic, if you recall, the cosine hyperbolic x is e to the power x plus e to the power minus x over 2. So that's 1/2 e to the power x plus 1/2 e to the power minus x. And here in a picture, I have drawn 1/2 e to the power x and 1/2 e to the power minus x. And if you add them together, you find the graph of the cosine hyperbolic. So that's this red graph that you see here. And similarly for the sine hyperbolic, the sine hyperbolic is a half e to the power x minus a half e to the power minus x. So if you add these two graphs together, then you find this graph for the sine hyperbolic. So this is what these functions look like. If you have cosine hyperbolic, sine hyperbolic, then probably you feel coming that we also have a tangent hyperbolic, which is sine hyperbolic over cosine hyperbolic. And the function, well, just go back to the definitions. So that's e to the power x minus e to the power minus x over 2, that's sine hyperbolic, over e to the power x plus e to the power minus x over 2, that's cosine hyperbolic. So you can write this thing, let's go here, as e to the power x minus e to the power minus x over e to the power x plus e to the power minus x. And what you can see from this formula is that for x equals 0, you find 0. So it goes for the origin, as you can see in the graph that I drew here. But what you also see, if x becomes very big, then the limit for x going to infinity tangent hyperbolic x is the limit x going to infinity. And then we have this expression here. Now if x becomes very big, then e to the power x is going to infinity. So what I'm going to do is I'm going to rewrite this equation a little bit as e to the power x over e to the power x minus e to the power minus x over e to the power x over e to the power x over e to the power x plus e to the power minus x over e to the power x, which equals the limit x is going to infinity, 1 minus e to the power minus 2x, 1 plus e to the power minus 2x. And what you see is if you let now x go to infinity, e to the power minus 2x goes to 0, so the whole thing goes to 1. So as you see in the graph, it has a horizontal asymptote for x going to plus infinity, and in a similar way you can show that it has also an asymptote for x is going to minus infinity. So this is the graph there. Okay. Now the last bit is a nice application of these functions. So why are they introduced? Why do we use them? So you can show that the shape that a hanging chain has, so think of your bicycle lock, if you keep it at two ends, and here you see different examples. So here is a little gate, and here is electricity wires, and here is a spider's web. All of these things take the same shape, and that shape that you see there is the cosine hyperbolic function. So all of these shapes can be described by this graph. A times cosine hyperbolic x over a. So for different values of a, 5, 2, and 1, you see the shapes here. And here I extended these graphs a little bit. So this is the shape that a chain will have. So you can show that a chain will assume this shape if you just support it by the two ends, and then it takes on this form. Now, if you know that, then you can also use it. And Gaudi did that in the designs that he developed. So if you think about a brick wall, if you're constructing a house or whatever, you know that a brick wall can withstand vertical forces much better. So it's very strong if you push on top or on the bottom. But if you push from the side, then it's not so strong. A chain, on the other side, you can pull that very much, but if you move it from the side, then it immediately changes shape. Now what you can do, and what Gaudi did, is take such a shape and then invert it, and then you get a very strong arch. So here is a picture, and it used to be on the book, from the Gateway Arch in St. Louis, Missouri. And this is not a parabola shape, but it's a cosine hyperbolic shape. So here you see in reality how you can use that. And Gaudi used that. So what he did is in his designs, he made constructions like this and like this, and he inverted them. So here you see that there is a mirror below it, so this is reflected, and this is what was actually being constructed. And for instance, for La Sagrada Familia, there are statues there because it's a church, as you may know. And then he put on little bags there to mimic the weight that the statue would have, and then he would invert it, and then that would be constructed. So that's a practical application of the cosine hyperbolic function. So let's leave it at this for the moment. It is 11:30, so we'll have a 15-minute break. I'll look at your questions in the meantime, and we will continue in 15 minutes. So see you in a bit. So let's start again. Before the break, there was still one question from Canvas that I left unanswered, which was from section 3.3. That is a bit detailed, so probably it's best if you email the question, show me what you tried for the solutions, how far you got for the person who asked the question, and then I'll answer to that. Also, I don't have edition 5 of the book at home. It's at university, and as you know, I'm probably not going to be at university for a bit of time. So if you also include a photo of the question, that will be great. So I'm not going to do that now, but I'll happily answer any emails that you have on that. So let's go back to where we were. So we were talking about this cosine hyperbolic shape and how Gaudi used it in his buildings. A couple of years back, I got an email from a person who said, well, I am a student, but I'm not a student at Eindhoven University of Technology. However, one of my friends is studying at Eindhoven University and he is attending your calculus classes. So this guy was studying law or economics, I'm not sure, but he was having a talk with his friend from high school, and he was laughing because he still had to study mathematics, whereas the guy who sent me the email did not have to do that anymore. And they made a bet. So he said, well, I'm going to bet with you that there is going to be a question in your calculus final exam on the railway station Veenendaal de Klomp. So also named the Klomp by the people living there apparently. So he asked me, can you put in a question in the exam on the railway station of Veenendaal de Klomp for me? And you shouldn't, of course, tell my friend. And if you do that, then I'm going to have a nice bottle of vodka afterwards. So, of course, so this is an exam question from a couple of years back. So we made a question about the 160th anniversary of the railway station Veenendaal de Klomp, where we have to design a huge banner for the railway station. So we assume that the banner has the shape of a cosine hyperbolic, and assuming that the banner has to be 40 meters wide, 20 meters high, compute the coefficients in this equation. So try to solve that. It's an exam question, so it's a good exam preparation. If you do not manage, let me know, and I'll put up the answers later on as promised. Okay. So last bigger topic for the day is linear approximations of functions and applications of that. So first of all, tangent line. Well, you've seen that time and time before. If you have a general function, y is f of x, the red graph here, you can pick any point on this graph, like here, and then you can draw the tangent line. So that's the black line that you see here. We know that the slope of this line m is the derivative. So m is f prime of x0. And then if you also use that this point x0, fx0 should be on the line, you have the equation of the tangent line. Now, the next idea is that if you are close to the point P, then the black line and the red graph are almost on top of each other. You can already see that in the graph. If you're close to P, then the black line is a very good approximation of the red graph. If you move further away from the point, it doesn't hold anymore. So only in a very, very tiny neighborhood of the point, it is a good approximation. Yeah? So if you would like to find the value of the function at a point x1 close to x0, maybe you could use the black line as an approximation there. And that is called the linear approximation. So Lx, this is just the equation of the straight line, of the tangent line there. So it's f prime x0 times x minus x0 plus f x0. That is precisely the equation of the black line. Now, how can you use that? Well, here's an example. So in the blue box, it's just the same equation from the previous slide. But here we are being asked to give the approximation of the cubic root of 8.02. And now the idea is that we do know what the cubic root of 8 is, because that's 2. 2 times 2 times 2 equals 8. So if you're close to 8, like here, then you could use this black tangent line as an approximation. So how does that work? Well, what we need is we first define the function cubic root of x. Then we will use the linear approximation at x equals 2. Now, f of 8 equals 2. And the derivative, well, just differentiate this thing and this is what you will get. So now we can write down the equation for the linear approximation. So this function L of x is the derivative times x minus 8 plus f at 8. And if you do the calculations there, this is simple algebraic calculations, you see that this is apparently the linear approximation close to x equals 8. The tangent line at equals 8 of the graph. And if you now plug in 8.02, you would find this as an approximation for the cubic root of 8.02. And just for fun, I also punched in on the calculator what the true value is. And you see that the true value has digits 1665 here, and our approximation has 1667. So that's actually quite good. It's quite accurate. Another example. If you look at the sine function that you know and love, that's the red graph here. You could also look at the tangent line at x equals 0, and that's going to be an approximation for values close to 0, so for small values of x. So how does it work? Well, f0 equals 0, the derivative is the cosine at 0 equals 1. So what we find for the linear approximation L of x equals x. So apparently for small values of x, the sine of x is approximately equal to x. And in a sense that shouldn't surprise you, because last week or the week before, I cannot remember, we have already seen that the limit of x going to 0 of sine of x over x equals 1. And here you see one of the reasons why this holds true. If you make x very small, then sine of x is approximately x, so the limit is going to be 1. It is not a full proof, but it's a kind of argumentation or a bit of understanding why this holds true, why the standard limit that you can use without proving it, that this is true. Okay? So the conclusion is sine of x is approximately x if you're close to 0. I have one more very nice usage of the linear approximation, which is I'm going back to the problem of zero finding. So we've already seen that. We've already talked about bisection before, where we were looking for this point alpha, where the graph crosses the horizontal axis. We have seen that sometimes it's easy. So if you have like a straight line or you have a parabola, then it's easy to find that point. But even for very simple functions like here, you cannot do that analytically. You cannot find an analytical expression for the zero of the function. So what we discussed back then is bisection, where you start with an interval that has below the graph above. The graph is below the axis and above the horizontal axis. And then based on continuity, that's why we talked about it, you know that it has to cross the axis somewhere. And we were going to make that interval smaller and smaller. And we did that by choosing the midpoint. And based on the function value at the midpoint, we shrunk the size of the interval. We made it half the original size. And if you repeat that a couple of times, then you find an approximation of the zero of the function. Okay. Now, we did that back then for the square root functions, x squared minus 3, to find a numerical approximation of the square root of 3, 1.7, and so on. And what we found back then is, oops, that was a bit too fast. I'm sorry about that. Let me go back to where we were. 1 second. We were here, I think. Like that. So what we found back then is that you would need quite a few steps to find an approximation which is not very accurate yet. So let's try with the mathematics that we have covered in the meantime to get to a faster method, which is called Newton's method. So let's see. Let me get a little bit of water. So as an alternative to that, I'm going to describe Newton's method, which is based on linear approximation. And Newton's method is the standard way to do this. So if you have a graphing calculator and you can plug in a formula and ask then where is it 0, for which x values is it 0, what it uses is Newton's method, some version of it. I need a bit more water. Okay. So, I'm back. So let's see. We have a function y is f of x, the red graph here. And we are going to try and find this point alpha, where it crosses the axis. And what I'm going to do is pick any starting value. So maybe you have a little bit of knowledge, or you can sketch a graph. You know approximately where the 0 is located. So we have some initial approximation x0. And what we do is use the tangent line, the blue line, which is basically the linear approximation. And where it crosses the axis, this x1, that's my next approximation. And then I'm going to repeat the procedure like before. So at x1, again, I draw the tangent line, which is the green line here. And from this picture, what you already see is that the x2 that we have then, so that's where the green line crosses the axis, is already quite close to alpha. I cannot draw one more because it just doesn't fit in the picture. So this example already illustrates that this might work a bit better. So let's see if that holds true. So the general formula, if you would like to implement this in a computer program, works like this. We have to find the tangent line. So we have to find the tangent line y is mx plus b at some point p. Well, we know the formula, we already derived that. So the slope is f prime x0, and then we know that it goes through the point p. So we have the formula here. And then we have to find where it crosses the horizontal axis, and that is x1. And x1 is apparently this thing here. So x0 minus fx0 divided by f prime x0. So this is a bit fast, of course, this derivation that I showed here. But basically you're just drawing the tangent line and you're trying to find where the tangent line crosses the horizontal axis. That's what's happening here. Now, let's see for our example how this works. So I'm going to look at the same example. So my function is x squared minus 3. And we're trying to locate square root of 3. Now, we already know that it's 1.7 approximately. So as a starting value, what I'm going to do is I'm going to start with 1, which is not really close, but sufficiently close. And then I'm going to do this iteration here. So I'm going to compute xi plus 1 from xi. So in the beginning, x1 from x0 by using the formula that we just derived on the previous slide. Now, if you do that, and if you compute those, you will find 1, 2, 1.75, and so on. And what you see is that you get very, very fast convergence here. So the number of correct digits, so the digits that say the same, it goes up quite fast, as you see. So here in only 6 steps, we already have a very good approximation of the square root of 3. So this works quite well, and that's why it's the standard method to do so. You can show, if you're into numerical mathematics, that basically the number of correct digits that you have, it is being doubled every time you do another iteration step. But that's beyond this course, but that's what I normally work on, so I can't resist telling you. So we have now seen the bisection method to find zeros and Newton's method. And what we have seen is that this bisection method, that's always going to work. So if you have this interval that contains a 0, you're going to find an approximation of that 0. it can be quite slow. So you need quite a few iteration steps, quite a few steps where you shrink the size of the interval to get an accurate approximation. Now, Newton's method, it doesn't always work. And maybe if you think a little bit about that, if you would have a function like, for instance, the cosine, you see that there is parts where it has a horizontal tangent line. Now, if you would be very unfortunate and you would try to start, for instance, your Newton iteration at a point where you have a horizontal tangent line, it's not going to work. So if it works, it's very fast. And what you also see is that you also need the derivative. So if you want to find the zero of some function f, you will have to compute the derivative f prime to do Newton's method. So as a next application, but a more theoretical one of linear approximations, we are going to look at L'Hopital's rule. Now, you may have already seen this in high school at mathematics. So let's see how it goes. So here is a very big blue box, but it's not that complicated. So let's see what happens. I'm going to give examples in a second. So it's another way to find limits, and then in particular limits of what is called indeterminate forms, which is like 0 over 0, infinity over infinity, if you would just plug in the x value. So let's say that we have an interval a, b, and a point in the interval. Now, we have two functions, f and g, and we're going to look at the limit of f over g. So basically, we have numerator over denominator. The numerator is f, denominator is g. And we're going to assume that they are differentiable. So we can compute f prime and g prime for all the x values in the interval, possibly excluding this one point c. So c is like the difficult point where these functions can be 0 or maybe infinite or whatever. But outside of this point c, they have to be differentiable. Now, assume that g prime is unequal to 0, otherwise, well, it doesn't hold anymore. For all x in the interval except c, because c is always excluded there. Now, if the limit has the form 0 over 0 or infinity over infinity, as you see here, and if you would differentiate numerator to get f prime, denominator to get g prime, and if this limit is either minus infinity, infinity, or some number L, then the values will be the same. So this limit of f over g is the same as the limit of f prime over g prime. So that is the whole definition. What is important to remember is that you should have something of the form 0 over 0 or infinity over infinity. So those are the situations where you can apply L'Hopital's rule. So let's look at an example. So how does this work? So if you have this limit, 1 minus cosine x over sine x. So x is going to 0. First thing that you try is to plug in x equals 0. And you find numerator is going to be 0 because 1 minus the cosine of 0 is 1 minus 1 is 0. Denominator, sine, is also going to be 0. So we have 0 over 0. And we cannot say what the limit is going to be yet. However, we can use L'Hopital's rule because, so first we have to check that they are both 0. So we have 0 over 0. Then we would like to use L'Hopital. So you see that both of them are differentiable. That's one of the conditions. G prime x, so g x equals sine of x. You see that g prime is the cosine, and that is unequal to 0. So what you can now do is replace the integral of f over g, so f over g, with f prime over g prime. So this is not the quotient rule that we're using. So we're not differentiating f over g, because then you would get f prime g minus fg prime over g squared, stuff like that. We are just separated. We are differentiating the numerator to find f prime, and we are differentiating the denominator, and we are looking at f prime over g prime. So not the derivative of the whole quotient, but just of the numerator separately and the denominator separately. So we replace that by f prime over g prime. Well, differentiating this thing gives a sine. Differentiating the sine gives a cosine. And now we can plug in x equals 0, and we find the complete limit to be 0. Let's do one more example. Here is the summary. Summary, and also, once again, the standard limit that we considered before, and before I just told you that this equals 1, we can now actually compute it using L'Hopital's rule. So it's f over g, we differentiate to get f prime over g prime. If we differentiate the sine, we get the cosine. If we differentiate x, we get a 1 here. And now you can plug in x equals 0. And here is the proof why this limit equals 1. So now we know that. Then one more example. I was already running ahead. So here we see something interesting occurring. If you look here, we have infinity over infinity. And then we can also use L'Hopital's rule. So there's two situations, 0 over 0 or infinity over infinity. This is the second case. So we are going to define the numerator to be f, denominator to be g. And then we want to check L'Hopital's rule. So we see that they are differentiable. Compute the derivatives. See that g prime is unequal to 0. That was one of the conditions for L'Hopital's rule. And you see that we replace f over g by f prime over g prime. So x squared, if you differentiate, you get 2x. The exponential function, you get the exponential function. And now something interesting happens, because after every step you try if you can already take the limit, if you can already plug in x equals, well, x going to infinity. And here, once again, we find infinity over infinity. So we have to do L'Hopital again. We have to do it twice here. So let's do that. So we're going to differentiate once more, and I'm not going to take the many in between steps here. So I'm just differentiating this thing to get a 2. I'm differentiating e to the power x to get e to the power x. And you can see that now we can take the limit and we find 0. So the original limit was apparently equal to 0 with applying L'Hopital twice here. So the most important message, if you want to apply L'Hopital's rule, is that you should have this form of 0 over 0 or infinity over infinity. If you have like 0 over infinity, that's going to be 0, right? If you have infinity over 0, that's going to blow up, that's infinity. So only these indeterminate, these cases where you don't know what's going to happen, that's where you can apply L'Hopital's rule, 0 over 0 or infinity over infinity. Now sometimes a limit is a little bit disguised and you have to rewrite it to get to that form. The next example shows this. So here, let's see what we have. We have 1 over ln x plus 1 minus 1 over x. Now if x is going to 0, then you get here the ln of 1, and ln of 1 equals 0, right? You have the ln function that goes like this. Y equals ln x. And you know that for x equals 1, the ln is 0. So if we have ln x plus 1, then if x is close to 0, we get the ln of 1, and we have 1 over 0. And of course, this is also going to be infinity. So this is infinity, and we have something like infinity minus infinity. And well, that can be anything, any number that you would like it to be, it can be. So we have to do a trick here. We have to get to this form where we can use L'Hopital, which is either 0 over 0 or infinity over infinity. Now, if you have two terms here, like you see here, and you have to do some rewriting, well then hopefully you will get the idea to combine them, to give them the same denominator and to make it one fraction. So let's do that. So so we cannot use L'Hopital. And we are going to rewrite. So I'm going to give them the same denominator, x times ln x plus 1. And if you combine them, then you find that you can rewrite the limit just using algebraic manipulations as this. X minus ln x plus 1 over x times ln x plus 1. Now, I'm going to call it f and g. And if you plug in x equals 0, you see that both of them are going to be 0. So now we have 0 over 0 and we can use L'Hopital's rule. So I'm going to compute f prime and g prime. See that they are both differentiable and also that g prime is unequal 0 for x around 0. And now I'm going to replace the limit of f over g by the limit of f prime over g prime. And what you see is if you plug in x equals 0, we still have 0 over 0. So we're not done yet. We have to do L'Hopital again. So first I'm going to simplify it a little bit. So this is what we found in the previous step. I'm going to multiply with x plus 1 over x plus 1, so multiplying with 1 basically to get it to a bit of a simpler form. Then we have the expression that we find here. You see that in the numerator I have x plus 1 minus 1, which is simply x. The denominator is going to be this thing here. And now we have 0 over 0, so we're going to apply L'Hopital again. So we're going to differentiate once again in the numerator and the denominator. Well, differentiating x, that's going to give me a 1. Differentiating the denominator, if you just do the computation, you will find this expression here. And now we see that we can substitute x equals 0. We can take the limit and we find that it is 1/2. So this is how it works. This is how L'Hopital goes, and you see that there is two basic ideas or basic complications that you should recall. One is you should have the standard form 0 over 0 or infinity over infinity. That's one thing. And the other idea that is important is that you need to rewrite if you do not have that form yet. So here's one more example. And this one is a bit more complicated. So here we have the limit. X is going to 1 plus, so from the right, from above. And then we have x to the power 1 over x minus 1. And then we get something like 1 to the power infinity. This is ugly and horrible, and we're not sure what's going to happen there. Also, it does not have the form 0 over 0 or infinity over infinity. So I need to do a trick here. So what is the trick? Now, the trick is that we have this complicated exponent here and we would like to get rid of it. So how can you get rid of it? Well, taking logarithms. We've already seen that. So I'm going not to look at y itself, but I'm first going to look at the ln of y. Because if I compute the ln of y, then I can write the exponent here in front of the logarithm, and then I've got a much nicer expression. Because if you look at this thing here, and you let x go to 1, then you have 0 over 0, and we can use L'Hopital. So I'm going to first compute a different limit. I'm going to compute the limit of ln y, and that is this limit here, and I can use L'Hopital. So using L'Hopital and differentiating in numerator and in the denominator, you see that I find 1. So what I have now found here with these steps is that the limit for x going to 1 plus ln y equals 1. Now, if ln y goes to 1, then y itself has to go to e. So that is the last step. The last step is that y itself goes to e. And you can see that as I just did by saying that ln y goes to 1, so y goes to e. Or alternatively, you could say, well, y, I can write it as e to the power ln y. I have now found that ln y goes to 1, so apparently e to the power ln y goes to e to the power 1, which is the same as e. So that is the limit of y itself. Now here's a few more test questions that I urge you to try. They're in line with the book and with the online questions that you get. So I will provide you with answers later on, but try to solve them first, and if you run into difficulties, please let me know. Then the last topic for week 5 and for today is sketching the graph of a function. So we already looked into that before when we were studying asymptotes and limit of functions going to plus or minus infinity. In general, if you're being asked to sketch the graph of a function, there is a couple of steps that you would do. So first you would look at the domain of the function. For which x values is your function defined? Then you would check for asymptotes. So vertical asymptotes is where, for instance, the denominator becomes 0. So this is where you might find a vertical asymptote. So isolated points where f is undefined, goes to plus and minus infinity, and so on. You study the first derivative. You make a sign chart so you know where it has local maxima and minima. You also know by a sign chart where your function is increasing, decreasing, and where it has horizontal tangent lines and possibly local extrema. So they may occur where f vertical tangent lines can also occur where f is defined but f prime is undefined, like the square root function. There you have a vertical tangent line at 0. And you would check if there are any horizontal asymptotes. So what does your function do for x going to plus or minus infinity if the function is defined there. And finally, you would like to check where it crosses the horizontal axis and where it crosses the vertical axis, and that's at f0 for x equals 0. So as an example, a function we have seen before, x squared over 4 minus x squared. First the domain. The domain is, well, everywhere except where the denominator becomes 0, so that's at 2 and minus 2. Then asymptotes. We've studied this example before, and we have seen that you should consider the limits around 2 and around minus 2 and 2, sorry. And then from the left and from the right, because the function behaves differently there. Then you would have to consider the first derivative. So if you compute f prime using the quotient rule, you find that this is the expression. You make a sign chart, so you see that something special happens at 0 and at plus and minus 2. So this is a sign chart of f prime. It is undefined at minus 2 and plus 2. It is 0 at 0. And if you plug in values to see what the sign is, you find minus, minus, plus, plus. So that means that the function itself is going down, and going up, going up. And finally, you check for horizontal asymptotes. If x goes to plus infinity, then you see that this function goes to minus 1. And for minus infinity, you see that it goes also to minus 1. Finally, the intersection points with the horizontal axis, well, your function equals 0. That's only for x equals 0. And for f, if you plug in x equals 0, you find 0. And based on all the information we have now, you can sketch the graph of the function, and you will see that it goes something like this. So it has horizontal asymptotes here, and for x going to plus infinity, and there is 2 vertical asymptotes. So, quick overview, what we have seen this week. Hopefully you checked the introduction video. We have looked at exponential functions and logarithms. Then today we have looked at sine hyperbolic, cosine hyperbolic, and seen that the cosine hyperbolic is the form that a chain assumes under its own weight if you support it at the 2 endpoints. And linear approximation, we have seen basically a couple of applications. We have seen Newton's method. We've seen how you can use linear approximation to approximate the function itself. And we have been looking at L'Hopital's rule. So that concludes the material for this week. Let me have a quick look in the chat room if there are any questions that I should answer now. So for the midterm, there is where you can type or upload your solutions to the questions. So the way it will go is you have a question, then there is multiple choice answers, and you choose the correct multiple choice answer. And there is A and B part to a question. So A is the multiple choice part, B is the solution that you wrote down on paper or that you type. So you can choose either you type it there or you upload it, and the uploading can be after the exam. And then there is a question if you can use long division. So if you have a polynomial of degree 3, 2 times x to the power of 3 minus 7x squared plus 9 equals 0, something like that, you can use long division there. If you know how that works, I didn't treat it because it's not that important here in the course, and you can do the trick where you find 1, 0 and then see what the rest polynomial is. So you can choose, if you know how to do long division, you can use that. That's fine to use. And then there is a new question popped up. Can we have a local min-max at an endpoint? Yes, that can happen. So if you have like e to the power x and you consider that on a certain interval, then you have a local and a minimum and a local maximum. So that concludes what I wanted to tell you about today. If you have any further questions, let me know. Just email me. And if you have questions for the next lecture, put them on Canvas. I will go through the questions again on Monday. I wish you a great week, and I'll see you in week 6. Good luck with your midterm test. Prepare well.